So this is joint work with Sarah Haney from Michigan, and we'll talk about the topic of wave kinetic equation, general like wave turbulence theory, which there has been a lot of activities recently. And so we'll briefly describe like what this theory is. Essentially, the idea is you take some like a nonlinear system of interacting waves, for example, like a nonlinear Schrodinger equation or water wave equation or something else you can think of. And then you consider this this system like with in the pseudo limit, the so-called large box weak nonlinearity limit, essentially having like lots and lots of like interacting modes, number of modes going to infinity, and you consider this so-called ensemble like of solutions under some particular like canonical distributions, like random, like a distribution of random initial data. And then you take pseudo limits, you study the evolution of the ensemble averages or so-called observables, and you consider the evolution of these quantities in the limit. And in the limit, they're expected to satisfy some particular effective equation, which is called the wave kinetic equation. It's essentially, you can think of it as you describe the behavior of the evolution of generic functions at a particular scale. Okay, so this is like some like old business starting from 1920s, and there has been a lot of like progress in terms of physics. Like it's like the basic equations were formally derived in 1920s, and then some for this like has been for water wave in 1960s and so on. And there has been a lot of progress in the like physics, from the physics point of view. Especially they're looking at specific like behavior of such effective equations, which we'll see later in later slides. And they are looking at specific behaviors and specific solutions, which they call the Kolmogorov-Zakharov spectrum, and essentially what they mean in terms of physics and so on. But so problem like we are looking at is the actual derivation, the rigorous derivation of this effective equation. Okay, so this is the big like the general description. So this is in parallel, somewhat in parallel to derivation of Boltzmann's kinetic theory for the many particle system. Here we're considering like many wave like interacting many mode interacting wave systems, and so both from the very like high level point of view, you can think of both as examples of the so-called Hilbert 6 problem. And so in this talk, we'll focus on the cubic nonlinear Schrodinger equation, which is the equation where this problem was first studied, and it's a simple but important model case. Of course, the method can also be applied to other systems, and in the end, we'll talk a little bit about the water wave system. Okay, so we start with the cubic nonlinear Schrodinger equation, which is this. So here we have lambda square, which marks the kind of the strength of the nonlinearity, what we'll see below. And this beta essentially it's a twisted Laplacian, which corresponds to a Laplacian like not on a standard square torus, but on a like a twisted like a rectangular irrational torus, which we'll see actually it makes a difference whether this beta is rational or irrational. And here we're considering a large box where we have torus of size L, and assume a dimension is at least 2. So of course here we can think of it as this in this setting we have a large box, or we can rescale it. We reduce an equation on torus of unit size, but then we have some slightly different initial data, which is which has first of all like L size of torus. So here in this setting we're having the Fourier variables are variables ranging in integer multiples of 1 over L. So it's like a mesh of size 1 over L in the frequency space. And then we assume the solution has first of all like k less than 1, which is like at a particular scale, and assume the mass is of size 1. So alternatively, we can study this on the standard torus, but then the frequency of size L, and then you have L to norm being like L to the d over 2 or something. But anyway, so we'll look at this setting like the large box setting. Okay, so this twisted Laplacian is this one, which corresponds to a standard Laplacian on irrational torus, irrational rectangular torus. So we'll see later on that this makes a difference in terms of time of existence. Okay, so instead of considering individual solutions, we're considering the ensemble or like a family of solutions that satisfy a specific law. And this is again consistent with the idea of kinetic theory, where we consider distribution of these many particles. And so this specific law, of course, is not something arbitrary, and we are trying simulating an idea where you have like a generic or random like solution that is supported at a particular frequency scale. And so what we do here is that we take some Schwarz function, and then we consider these kind of initial data where you have the Fourier coefficients are independent, like identically distributed, not identically, right? So this either k are independent, identically distributed, like random variables, and these, and then you have multiplied by some like a prefix, like Schwarz function. Essentially, this Schwarz function is something you just a Schwarz function supported at scale 1. Okay, so that's what happens. Like you choose a nice Schwarz function scale supported at this particular scale, and then you randomize the Fourier coefficients, like you randomize Fourier coefficient by multiplying by some like random ID random variables, and this is a natural way to think of like a random or generic distribution of function that is supported in this particular frequency scale. So this is like the measure of size 1 over L. Okay, so this is the kind of the ensemble we're considering, and this either k and ID random variables, and so our result actually applies for a large class of such random variables, such distributions. So essentially, you only need these to be rotationally symmetric and have exponential tails. And so the physically significant choices are the choices of Gaussians, where you essentially have independent like Gaussian Fourier coefficients, which means it corresponds to a infinite dimensional Gaussian measure on the space of functions you are considering. So this is of course a like canonical object. Another choice is you consider this so-called random phase setting, where you have the size of the fix the size of the Fourier coefficients, and then you just think of the phase or the argument of the Fourier coefficients being a random, being a uniformly distributed on the unit circle. And this is also like from physical point of view, you just do random phase ansatz. So all these will follow from the same argument. Essentially, the exact distribution plays a little role in the analysis. So assume that these things have mean 0 and the variance 1. Okay, so by conjunction inequality, you can think of it like if you start with this kind of initial data normalized in this way, then you think of the L2 norm of the initial data is like about L to the minus D over 2. Like if you just think of the L2 norm, which is obvious, and then by conjunction inequality, we know that if we have essentially a function with like independent Fourier coefficient, then L infinity norm and L2 norm is essentially almost surely like comparable. And then so then you see the L infinity norm of this initial data would be of size L to the minus D over 2. So this is the initial data. Oh, sorry. So, this is the initial data. This initial data, and the size is like L to the minus D over 2. So if you think of it, like the strength of nonlinearity is essentially the the nonlinear part, nonlinear contribution divided by the linear contribution, which in this case is just lambda squared times mod u squared. And if mod u L infinity norm is like L to the minus D over 2, then the size of the strength of nonlinearity would be like lambda squared times L to the minus D. Which you see here, and we define this to be alpha, which marks the strength of the nonlinearity. And in the limit we're just describing, so we're considering the limits where you have this so-called large box where L goes to infinity, and the weak nonlinearity where alpha goes to 0 in this limit. And we're interested in the evolution of these expectations, these ensemble averages, like the size of the Fourier modes. Essentially, it tells us, like, if we know something about this, it tells us essentially, like, if you have generic initial data evolving under the nonlinear Schrödinger's equation, then what would happen, like, what would happen to the size of the Fourier modes in the pseudo time scale, essentially, like, what happens in terms of this energy shift, like, between different Fourier modes at a particular time scale. Okay, so there has been heuristic calculations, as I said, like, starting from 1920s, and they have derived, like, formally derived, like, a well-known equation, which is called the Webcam Equation. And it's essentially, it tells us that these quantities, this expectation, they are going to evolve, like, under a rescaled version of this Webcam equation, which for tau is rescaled time, and this equation is essentially this one. So you have the right hand side is integral, like, over, like, k1 minus k2 plus k2 equals k, and have a delta of this factor, which is called the resonance factor, which you'll see it again later on. And you have this nonlinearity, which is essentially like a cubic nonlinearity, and of this form. Okay, so here this mod k, like a beta sub beta, which means is the quadratic form associated with the twisted Lagrange. Okay, so this is the idea of physicists, and they conjecture, they expect that in the pseudo time scale. So we'll see the time scale in a minute. And at a pseudo time scale, the evolution of this quantity should be seen from this Webcam equation. Okay, so this is this conjecture. So essentially, if you consider this nonlinear Schrödinger equation with the random initial data described above, define this kinetic timescale, which they conjecture is exactly this alpha minus 2, which is the lambda to the 4 times L minus D. So this is what they conjecture to be the kinetic timescale. Then the expectation of this, this size of Fourier modes is given, like, approximated by this the solution to the Webcam equation after rescaling by this T kinetic. So T, like, less T between 0 and some constant times the kinetic timescale. So essentially, it tells us that the evolution of this quantity is given by the solution to the kinetic the Webcam equation. Okay, so n tau k is solution to the Webcam equation, and this O1 is a quantity that goes to 0 uniformly. And so this should hold under suitable limits along which this L goes to infinity and alpha goes to 0. And actually, it's important, like, to quantify what's the relation between L and alpha, and we'll see that there is natural conjecture of what would happen, like, what would make this approximation valid. Okay, so essentially this corresponds to establishing, approximating the evolution of these ensemble averages by the effective dynamics of Webcam equation up to time tau equals tau 0. And we will say we justify the Webcam equation up to time up to this time. And I must remark, as of now, like, even with the result I'm talking about, this conjecture is still open, even for short time, like tau 0 less than 1. So in all these existing results, this tau 0 will depend actually on L alpha, and actually goes to 0 in the limit. Although it's like it goes to 0 almost only like alpha minus epsilon for n arbitrary small epsilon, it still goes to 0. And it would be a major, like, a goal in this direction to actually establish this conjecture for tau 0 independent of alpha tau 0 being a fixed, even a small constant. And this is actually we expect this to be much harder than everything that has been done so far, because that's like it's closing this last, even if we can, for now we can get to like at tau 0 equals alpha minus epsilon for arbitrary small epsilon, like going from this to the this last step is actually much harder than what we have done like before, because of the reason we'll talk about is essentially it's due to a criticality problem. Okay, and also conjecture may depend on the way in which L goes infinity and alpha goes 0. We'll also describe this later. Okay, so now we introduce the main results. Before we describe main result, we first describe like what was known before. Essentially, not too much is known like mathematically before, there was some results on simplified models, linear models, or other models. Like so, there was work of Erdős Shen Yao and with Sam Hofer, where they essentially dealt with the case of linear Schrodinger equations with like a fixed potential. And then there was this work of Lukarinen and Schwang, which they were deal with nonlinear Schrodinger equations, but on a lattice, not on a torus. And they were able to get some like pretty nice results in the limit. And for this conjecture itself, it was started actually started by the work of Buckmaster, Germain, Hani, and Chata, where they were able to they did like the case of I think 3D, and they were able to justify this wavelength equation up to time which is like essentially like L minus 3 times the kinetic time scale, and for certain ranges. So this is the first mathematically rigorous result, although you see it's quite far away from the thing that is conjectured. You're kind of getting to a very, very short time compared to the conjecture. Okay, so now this is the main result, which is joint works with Hani like from last year. So we're able to establish this Webcam equation, the validity of this Webcam equation up to time like L minus epsilon times the kinetic time for any arbitrary small epsilon, provided that this in this limit, this alpha and L satisfies some particular scaling law that is close to either alpha equals L minus 1 or alpha equals 1. Okay, so this alpha, I think the more important case is where alpha is close to L minus 1, and this is actually a natural limit in the case of a rational torus. If you have like a square torus, then this is actually a natural limit of when this Webcam equation can be valid. Okay, so this is a precise statement. So for a fixed epsilon, which can be arbitrarily small, and beta, so assume, okay, so here beta can be arbitrary, not rational, irrational, doesn't matter. And suppose alpha is like L to minus 1 minus epsilon over 2 plus means plus something much smaller than epsilon, or else you have alpha is comparable to L to the minus epsilon plus, then this then for t like up to time, like this is like technical, never mind. So for t up to time L to minus epsilon times the kinetic time scale, we have this approximation that this sum of average is approximated by the solution to Webcam equation plus something which is little O of 1 compared to the changes caused by here. So this, in fact, it's like a negative power of L, because we're in the so-called subcritical setting, so you can always have a room of a power of L. Okay, so this is the first theorem. The second theorem actually, so first theorem only concerns the specific scaling laws, like where it's comparable, alpha is almost L to minus 1 or alpha is almost 1. And the second theorem establishes like general scaling laws, although for general scaling laws, we're not exactly getting to the kinetic time scale. We're getting to something slightly weaker. So this is the time we're getting to some time t star, which is not reaching kinetic time scale, but it's something slightly weaker, and it also depends on whether or not this beta satisfies genericity condition. So whether we have generic irrational torus or we have a like a square torus, it also makes a difference. Okay, suppose this TR satisfies this, it's better see in the diagram which will show in the next slide, and also that T is less than L square for for arbitrary beta, and assume that T is less than L to D for generic beta. So these are natural limitations which has to do with exact resonances. Then the result of this Webcam equation can be justified up to this time t. Okay, so it's better seen in the diagram, which is this one. So essentially, you see this in this diagram. So this the x-axis is like a log L of alpha minus 1. The y is a strength on the nonlinearity, and the y-axis is a log L t, where t is the time. And then in this picture here, you see this red line is a conjectured like a kinetic time scale, like the one that conjectured where the Webcam equation should hold. And then this, like these vertical lines at D and at 2 are the kind of natural limits for in the case of for t equals L square, exponent is 2. This natural limit for like arbitrary torus, notably the square torus, the rational torus. And then the horizontal line, like t equals L to D, is actually the natural limit for generic torus. So this has to do with exact resonance, which I will not talk about. And then this red line is the conjecture, the kinetic timescale. And what we get in the main theorems is this the region bounded by the blue segment. So essentially, we get like something like not as good as the conjecture. However, we do get arbitrary close to conjecture at the 2 points here, where this this point, like the lower left point, corresponds to the case where alpha is almost 1, and we almost get the kinetic timescale. And this point, like where the coordinate is like 1 and 2, this corresponds to the case where alpha is almost like L to minus 1, and we get to the kinetic almost get to the kinetic timescale like t equals L to square. So essentially, our result, we're getting like to the almost kinetic timescale in 2 points, and in other points we also get something which is also improvement to the existing results. Okay, so let me make a few remarks. First of all, the error term is like O of 1 times this, which has to do with the fact that we are still not getting to a kinetic timescale. We're getting still kind of subcritical cases, and therefore this O1 has to be quantified to be much smaller than this change, like caused by the Webcam equation. But it's this technical thing, because the main contribution will be this, and this O1 times this quantity will be error term. Okay, and the result of theorem 1 and 2, you have seen it depends on particular scaling law between alpha and L, and in 2 cases we're almost reaching a kinetic timescale. Although we're not actually reaching it, we are reaching it up to like L to minus epsilon for arbitrary small epsilon, but it's like so we're almost reaching it. And this can also be compared to kinetic theory, where the Boltzmann equation is derived from the so-called Boltzmann-Grad scaling law, which is also a particular scaling law between the parameters between the parameters in the limit. So for the Boltzmann equation, is actually currently not really known, like whether this derivation is true, which derivation is valid, like for other scaling laws, and same case here. We also don't know, as of now, we also don't know whether these derivations are valid like for other scaling laws. We'll talk about this. So we'll have a few slides about this later. Okay, so extending will require subtle cancellation, which is currently still not fully understood. Okay, so we'll have to mention 2 related results by the works of Collard and Germain. So first of the result is around the same time as our work. They were essentially get the same result as we did but in a kind of more more specific case. So they were considering the square torus, and they were only considering this case corresponding to a scaling law where alpha almost equal to L minus 1, and in this setting they were able to get essentially the same result as we did, where you get to justify the Webcam equation up to time like almost like L to minus epsilon times the kinetic timescale, and so the result corresponds to this picture, this green part in the diagram, where it reaches this point like 1, 2, which is one of the things we get where we reach the almost like kinetic timescale. Okay, so this is essentially around the same time as our work, but it's of course it's independent. Okay, and more recently they were able to get something different. They were considering the case of generic irrational tori, but it's non-rectangular tori. In comparison, in our result, we are considering the rectangular torus, and they are considering, in the new work, they are considering the non-rectangular torus. And for such torus, they have been able to prove that the solution exists almost up to kinetic timescale, meaning its solution exists up to L to minus epsilon times the kinetic timescale for arbitrary small l. For more general scaling laws, well, in this case, the existing result essentially covers the whole conjectured region, like this whole region. They were able to prove existence. However, this result like only cares about existence, and it doesn't involve the justification of the Webcam equation. And this is due to some reason. Essentially, if you want if you want to calculate asymptotics, you'll need to look at the counting problem associated with specific differential equations and want to count, want to get like an asymptotic information of this system. However, if you just want to prove existence, you only need the upper bound of such system, and upper bound is usually much easier to deal with than the asymptotics. So because of this, they're not able to get to justify the Webcam equation, but they were able to get the existence also up to this time. So at least it's a suggestion that something can be said like up to this minus epsilon times the kinetic time scale, which suggests that this conjecture may, in any case, may be right. Okay, so now we move on to the sketch of the proof. So we have like 15 minutes maybe. Okay, so the idea is it's actually quite simple. So if you start with this random initial data, what you do is actually you just do the formal Picard iteration. You start with initial data, the linear evolution, and then you construct the second nonlinear evolution, the third nonlinear evolution, and so on. It turns out that this expansion will be a valid like asymptotic expansion for the solution. So we first write it in terms of this Duhamel form, and then we apply this Picard iteration to write u equals u0, solution u equals u0 plus u1 plus u2, and so on. And then u0 is linear evolution, u1 is the first nonlinear, u2 is second nonlinear. I don't want to write further, but you get the idea. Then of course we want to study, for example, at first we want to study the term u0, which is easy, and then the term u1. Okay, so this first nonlinear evolution. Like the point here is that each of these uj has explicit expressions, and then we can calculate exactly the correlations, like the correlation between this uj and uk. Because if you remember that what we want to prove, we want to look at is the excitation of the square or norm square of each for coefficient, and then we just, because the solution has this expansion, then we just essentially reduce to the calculating correlation of these quantities, and these can be calculated explicitly for each term. Of course, this is just the lower order term. Lower order term actually exactly gives the nonlinearity of the Webcam equation. So it's an explicit calculation that has been done actually before. Now, what about the higher order calculation? What about expansion? It turns out that these higher order terms are remainders, and it turns out this uj satisfies successively better estimates like as j increases. It turns out that this is a formula here. This rho here is a parameter that actually in like precisely rho is smaller than 1 or negative power in the setting, in the relation between alpha and t that we have. And then you always have this if rho is a negative power, then this uj are getting like better and better, and it has convergence like when j goes infinity. Okay, so let us explain like curiously why would we expect these things to get better and better? Like under what condition do we expect these things to get better and better? Okay, so the reason here is that, so if you look at u0 is just nothing but the Duhamel operator applied to this cubic nonlinearity. Then you just move to first space, you do some calculations, and this, it turns out, involve this integral of e to I omega t, where omega is the resonance factor, which is, so you'll see that the main contribution of this integral is coming from the case where omega is 0 or close to 0, which is so-called almost resonant case, which also explains why in the Webcam equation we're seeing this delta of this resonance factor, exactly because the main contribution is coming from the resonances or almost resonances. Okay, so and now you're having this, which is given by this, and you have this initial data, and then you have this products of independent Gaussians. So key idea here is that if you remove the degenerate contribution by so-called weak ordering, which is a standard procedure, the rest will enjoy a square root cancellation due to randomness, which you can think of the central limit theory. We have a sum of independent random variables. will be like a sum of n independent random variables will be size like square root of n instead of n, like due to the central limit theorem. And here is the same. You're summing over like these are products of independent random variables that have same properties. So then you see this sum would not be equal to the number of terms involved, but equals to the square root of number of terms involved, which is the idea of a square root cancellation, which is actually really a universal thing to think of in probability. And then this effectively changes the scaling of the problem. Okay. So we may assume that kj is less than 1 due to the the Schwartz initial data, and then the number of terms in the summation. So we won't omit the detail, but essentially do a dimension counting. The number of terms will be something like this. And then we calculate the size of the characteristic size of U1, which is this quantity. And we want to compare the first nonlinear evolution with the linear evolution. And we want the higher order term to get successively better. That means that the first nonlinear evolution has to be better than the linear evolution. So this has to be less than 1 precisely if t is less than this quantity, which is a kinetic timescale that we are considering. So this is a heuristic justification, like why we expect to see something like at this kinetic timescale, and that's precisely because of this. Like this is like essentially this kinetic timescale is longest time. It's the longest time while we can still treat the random data problem kind of perturbatively, like. In perturbative in some sense, in the so-called probabilistic sense. Okay, and this consistent with the notion of probability scaling, which is introduced in the recent works in the recent work I had with Andrea Namod and Haitian Yue, and we introduced this notion of probability scaling, and in this case, the probability scaling exactly corresponds to this kinetic timescale. Okay, so this a rough idea, like to where we go, and the proof essentially you can divide into like 5 steps. So it's like a general plan. So for first of all, we do these pick expansions like the U0, U1 up to U capital A for some suitably large capital A, and then W, the remainder will be error term, which is very tiny, like in the suitable space. And uj are these picker iterates. And we'll prove, of course, that these uj do satisfy better and better bounds in some form of access B space with high probability. And this is actually one of the main parts of the argument. We need to do all these combinatorics and analysis to get the bounds for uj. And so we're going to perform a fixed point argument for W to show that it has tiny access B norm. Provide A is large enough, and this actually we will see this has to do with another linear operator estimate, which we'll have to use a kind of a TD star argument. And once we know this, once we have the expansion, so actually let me mention that once we have this expansion, we're already able to justify existence, and that's essentially the case in the recent work of Kohler and Germain. They are able to perform these parts 1, 2, and 3, and they were able to get the existence. Now, in order to get asymptotics, we have to calculate the correlations explicitly, and turns out that the lower order correlations, like where j is less than 2, it gives a discrete version of the Webcam equation nonlinearity, and the high order version are in fact just error terms. And finally, we'll need a number of theoretic components so that we can approximate this discrete version by the continuous version, and we do get. And to show that we do get to the full nonlinearity of Wavelength Equation. And actually this has been difficult in the case of non-rectangular torus. And but in our case, in the case of rectangular torus, it has been done actually in previous works. In the previous work of Buckmaster, Germain, Hani, and Chateau. Okay, so this is in the rest the remaining 10 minutes, we're going to talk about this parts 2 and 3 essentially, which is the main thing that is done in this paper. Okay, so by the structure of equation, the idea is that each of these nonlinear iterates uj can be written as a linear combination of a so-called ternary tree terms, which is also a very common idea in the study of these nonlinear shorting or nonlinear Schrödinger or heat equation, or do a form expansion in terms of trees. And here T is a ternary tree with exactly 2j plus 1 leaves, and this sum is you're summing over all the k n's, where n is all the nodes, and you have this essentially this is the initial data, right? This is the initial data, initial size of initial data, and this is the random, independent random variables corresponding to the KL, where L's are the leaves. Okay, and this is some coefficient, like some coefficient we'll naturally see in the equation. Okay, and then this can be viewed as a variant of so-called Feynman diagram. So Feynman diagram, I think sometimes it's referred to as a correlations, but here we can also talk about the trees as a expansion involving like multilinear Gaussians. Okay, so this example of a ternary tree, you see like it's like K is the final output frequency, and it's broken into like K1, K6, and K2, which is 3 input frequencies, like by cubic term, cubic nonlinearity. And K1 is broken into like K3, K4, and K5, again by cubic nonlinearity. K2 is broken into K7, K8, K9, again by cubic nonlinearity. So then you see we're having all these frequencies, like frequency vectors, like Kj. Okay, and you have like K equals, and this is just because it's a product nonlinearity, it says like this on the Fourier is a convolution. And then also we have these resonance factors like omega J, which associate with this like these frequencies. And then in the end, it turns out that this ternary tree term is given by this multilinear Gaussian. So this sum over like all these vectors, and then you have this coefficient. And then you have this, this initial data times this random variables, and like multilinear like random variables. So the coefficient here turns out to have a decay like in these resonance factors, which we have seen actually before. Like here we have like 1 over omega, which is decays in the, this coefficient decays in the resonance factor omega. Okay. And then we're looking at this, this multilinear Gaussian like expression, and what we're doing here, we're going to estimate, the size of these multilinear Gaussians using the square root cancellation that we described above. Okay, so this coefficient has a pseudo decay. Essentially, you'll see like we have 1 over omega j decay, and in order to get the main term, we assume these omega j's are kind of small, where omega j is less than 1 over t, and then we define such factors to be admissible, and so essentially the effect here of this decay here is that we can reduce the summation where we only sum over these admissible vectors. So here we're summing over like admissible vector, we satisfy these equations, the linear equations, and these bounds for the resonant factors, like it's kind of the so-called resonant or almost resonant contributions. And we have seen that the main contribution, the Webcam equation, only like coming from these resonance or almost resonant terms. Okay, and then we talk about the pairing. So essentially, we would like to apply this like square root cancellation. However, if you have like pairs, where pairs means that we have some, for example, like some either ki equal, like either ki equals either kj or ki equals kj, and if the sums are opposite, if the signs are opposite, then we have like eta omega times conjugate of eta omega, which is like mod eta omega square, which is of size 1. You don't really gain any kind of cancellation. So you have to identify these pairings, and then for the rest unpaired like inputs, like input Gaussians, you can apply this square root cancellation. So you want to identify those pairings where we have this, for example, here is a pairing like K6 equals K7, here is a pairing where K3 equals K8. If we identify these pairings, and these pairings won't contribute to the cancellation, and the remaining things, the unpaired things, will contribute to cancellation. So this is like just a way to describe this, like describe this essay. So you see, the idea is that the main point of this work is that we're able to like really like decode all these complicated combinatorics, and we're really able to get this sharp like estimate for like for tree terms of arbitrarily big size. And this, as far as we know, hasn't been done like has not been done like in any of the previous works. Like they're not able to get sharp like sharp estimate for arbitrary arbitrary high order terms. Okay, so here we're identifying the pairings, which is like this, and we reduce to the case of so-called unpaired unpaired like terms, unpaired like nodes, and then we apply this square root cancellation. Essentially, this is the key thing. We are summing over the unpaired or single nodes, and we have the square, like the summing, the inside summing is no, there's no cancellation, but then on the outside summing, we're gaining from the square root cancellation. You know, by a simple like estimate, we're getting this sum here and this soup of sum. And this, you see, summing one is really just a counting problem. Like the result of a counting problem, we count all these factors that satisfy like a certain equalities and certain inequalities that we introduced before. Essentially, inequalities means that the resonance factors has to be small. In any case, you see we're reducing, in this way, we're reducing this like this size of the picker iterates to this counting problem. And for this counting problem, the main thing is that we are developing actually like an important, like a detailed like algorithm. Actually, how do we do the counting problem? Because we're involving this counting problem, this big counting problem involves like all these vectors kn, where n ranges over all the nodes of this big tree, big ternary tree, and we have to find a way like in what order do we count these vectors? We first fix some vectors, we count the vectors adjacent to it, and then count the vectors adjacent to those, and we have to fix like an order of doing so. And this has to be done very carefully in a detailed algorithm, like how exactly we do, what order exactly we do the vector countings. And so unfortunately, we don't have time to talk about this, but once we have we're done with the countings, then we can get to the sharp bounds for these counting problems. And this is eventually will lead to sharp bounds for the picker iterates that we were guessing, that we approved. Okay, so finally, let me just mention a little bit like how we close the fixed point argument for W. And turns out since W is supposed to have a tiny size, the quadratic term in W are fine. And the only thing you need to worry about is this linear term in W. And you just only need to worry about this particular linear operator, which is this one. And then you need to prove essentially like the L2 to L2 operator norm for this linear operator. And now there is a classical way of doing this is by a high order T star argument. Like for example, you think of the Stein lemma, like how this is proved, like by high order T star argument, and we just need to prove that to bound the norms of the nth power of the T star for sufficient large M. So the key thing here is that if you look at the kernel of this nth power of this T star operator, then it turns out that this can be written as in the form of a slightly different tree term. Where this tree has this specific form where you start with a node, you keep adding this like T1, T2, or T1, T2 is the subtrees, you know, appearing in this operator. And you keep adding this T1, T2. So this is kind of very specific tree structure. However, it still falls into category of a general tree estimate, and it turns out we can actually deal with this, like such terms, like using a general tree estimates. So this is like, and then you see we are by using this like general, we just prove this general like tree estimates from counting as here, and then we also get like a nice the good enough bound for these high order T star operators, and then in the end we this leads to the closure of the fixed point argument, and then leads to closure of the proof. Okay, so in just in 1 or 2 minutes, let me describe a little bit the case of a water wave. So the result, the method can also be applied to other models, and we'll describe a water wave, which is this ongoing work with Ionescu, Posteri, and Deng. And essentially, if you look at the water waves, which I'll not explain, and then if you can again consider like well prepared initial data, then you can also have you can ask like, well, how does these Fourier modes like evolve, and you can ask the same question. And the point here is that this nonlinearity of the water wave equation is formally quadratic, not cubic. However, it's a non-resonant one, so it's well known that this can be removed by normal form transformation, leading to cubic nonlinearity. So there's a very nice recent work of Berti, Fiola, and Posteri, where they in fact did one more normal form, like removing the non-resonant like cubic nonlinearities. But here, let's say we just remove the quadratic nonlinearity, then we get a QV nonlinearity, and the initial data will also be transformed, but in a trackable way, in the sense that the ensemble averages is kind of comparable for the transform and untransformed data. And then we can formally derive Webcam equation like from this QV nonlinearity, which has some similarity with the nonlinear Schrodinger equation. So this was a classical work of Hasselmann in 1960s. And of course, the question is like, how do we rigorously justify that? And here, main feature of water wave is that it's a quasi-linear instead of semi-linear. And because of this, we cannot really use SXSP norms. Instead, we employ a kind of quasi-linear strategy where we have this high order energy estimate and the kind of profile decomposition at low orders. And in order to do this, we may involve some kind of L infinity, like by Kinch inequality, or maybe like if we want to get to like better estimate, we may need some kind of like random matrix techniques. And this is something actually not that is not very clear. Like what's the optimal thing to do now. It's also related to the question of how do you prove like random data opposites for quasi-linear equations. Well, for semi-linear equation, we already have a nice theory, which is the so-called theory of random tensor that I had with Andrew Namo and Haitian Yue recently. But it's still not very clear what do you expect if you have a quasi-linear equation. That is one of the things that that makes a water wave problem interesting, and that's something that's worth looking at. So I'm a little bit out of time. I'll stop here. Thank you.